So looking at number 11, it's asking us to find the range of the given functions, expressing our answer in interval domain, or interval notation. So the first thing that we're going to want to do for this is to figure out the domain, right? At least if we're doing this algebraically. The directions don't dictate that you need to do it this way to show it algebraically, but let's go ahead and do that anyways, because that's what Katie was trying to do. So the implied domain here was obviously all real numbers. Again, there's no context to this problem. And the relevant domain also is going to be all real numbers because the only operations involved were squaring and addition, neither of which are going to ever present a problem if we're dealing with real numbers. The next thing we should do is we should take a look at the graph of our function to determine whether it's increasing or decreasing or whatever. So the graph is going to look something like this. Still doing good, Katie? So unfortunately here, when we look at this graph is both decreasing and it's also increasing. Everybody okay there? So ideally, we would break up our domain that we're looking at into a decreasing section and an increasing section and have to worry about each of those. Now, I can look at the graph and tell right away that, like, I just really need to pick one or the other because this thing is a mere reflection of the other, so all the y-coordinates on one side are covered by the y-coordinates on the other side. If you didn't notice that, though, it wouldn't make a difference. You'll get the same answer from each piece, so it's not a big deal. Are you good with this so far, Katie? Okay. And this was, I think, the piece that you missed, right? Because I think you used the original domain rather than the interval that was increasing or decreasing.
Yeah, I did.
Yep. So that, and again, I would have suspected most of us would have, right? We didn't see an example where we had a function that had both increasing part and decreasing part where you really had to worry about that. The whole thing was always increasing or decreasing, so we could just get away with not having to break up the domain at all. So let's say we use the increasing part because I don't have to flip the bounds when I calculate the range, right? The lower bound for the range just comes from the lower bound from the domain. So the lower bound for the range is going to be f of the lower bound from the domain, which is just going to be f of 0. So that's going to be -4. The upper bound for the range is going to be f of the upper bound for the domain, which is f of infinity. Now, infinity squared minus 4 is still infinity. And because we're dealing with an upper bound, the infinity I know must be positive. Everybody still okay? So my range here, f of x, is going to be a member of the interval from -4 to positive infinity. I know the infinity gets a parenthesis, but what is the -4 going to get? It's going to get a bracket because the -4 is coming from the domain, because the 0 is our domain value, not an interval from, it's not coming from the interval of increasing that it's not a member of. It's coming from the domain that it is a member of. So yes, this should be a bracket. That's a little bit much.
Yeah, good.
But here's the thing. The directions here don't state that you have to do this algebraically. So you could have just looked at the picture and written down what the range was going to be, right? Like, that's not wrong for the directions. Now, if I asked you to support your answer algebraically, yes, I would expect to see like this kind of stuff. But the directions here didn't ask for that. So you didn't need to do it that way, But it's a good thing to make sure that we can do it that way. Jack?
So just making sure you got the lower bound domain as 0 from the increasing section?
Yes. Yes. Yep.
Then, I just have a question.
Yeah, go ahead.
Do you mind doing number 8, please?
8? Yep. Are we good to move on, everybody? I just want to check before. Okay. 8 is that okay? So k of x equals x over x squared minus 1. Again, the implied domain here is all real numbers. Since there's no context to this problem, the x's don't really represent anything other than numbers. To find the relevant domain, then, the operations involved are division, squaring, and subtraction. The only of those that can present a problem is the division, because I know that when I'm dividing, I cannot divide by 0, so whatever the denominator if my fraction is, I know cannot be 0. So this is like a quadratic equation here. You can solve it by factoring or completing the quadratic formula, or just kind of solving it directly, adding 1 to both sides and square rooting, kind of whatever you want to do. I think that this one probably most obviously would have been done by factoring, since you had a difference of 2 squares. And then from there, it should be easy to see that the two solutions are x cannot equal -1 and x cannot equal 1. Jack, are we so far so good?
Yep.
Okay. Now here's a place where it's tempting to want to convert both these both of these into inequalities like we had done in the example. I would suggest we don't do that, because it makes it messier than it needs to be. So let's just think about this common sense wise. If we can have everything except for -1 and +1, that means we can have x's that are less than -1, right? Or we have the x's between -1 and +1. Or we have the x's that are greater than 1. Do you buy that? And then I can take each one of those and create my interval. So less than -1 is -∞ to -1. Between -1 and 1 is just -1, 1. And then greater than 1 is 1 to +∞. I have to cheat. Natalie.
This isn't about the math, but
okay.
When you write positive infinity, can you just write the infinity side?
Yes.
Okay.
Yeah, I always write it because it helps me not forget to do the -∞ if I'm always putting something in front. Right? It never that way I don't forget to do the negative, because I'm just always used to writing something in front of my infinity, but it doesn't need to be there.
Right.
You're welcome. Aim. Sure. Jack, we were good, right?
Yeah.
Okay. I just want to double check before we moved on. 22. Here we're asked to prove whether this thing is increasing, odd or even or neither, right? So let's just start by taking a look at the function involved. I have a degree 3 monomial minus a degree 1 monomial. Since the degrees for both of those are odd, I know that this should be an odd function. Right, Amy? So I know where I should be landing already. Let's go ahead and do the proof then. So they always start here with k of -x, or I really should say the function evaluated at -x. The function name is immaterial. So go ahead and plug in -x in place for all my x's. Now, -x cubed is -x times -x times -x. I multiply 3 negatives, I get a negative. I multiply 3 x's, I get x cubed. So this first term becomes negative 3x cubed. And then negative 2 times negative x is positive 2x. Just for your just for an FYI, if I compare these two right now, it's not equal to k of x, which tells me that this is not even. Everybody's good with that? Okay, so let's see if we can make it be odd. To do that, I have to factor out a negative sign. When I factor that negative sign out, all the signs flip. And if I compare this part to the original, they are the same. So the negative sign comes down, and then this piece is just k of x, which is what is negative k of x, right? Which is what we need to be odd. Does that feel okay, Natalie? Right, you asked this question. No. Who asked this question? Amy. I'm sorry. Jeepers creepers. That was a question behind her. 2 or 3? I don't even know anymore. It's the end of the day, guys. I'm tired. Okay. Thank you. I appreciate the Eddie.
How exactly did you get a negative k?
Okay. So the part that's underlined in green, that's identical to k of x, right? And then I have a negative sign out front, so that's the negative k of x. So the part in the parentheses is my k of x, and then I still have the negative sign out front that just comes down with it. That was what you're missing? Perfect. Mia?
Number 18.
Yes. Are we good with 22? Okay, great. 18 is a all on the calculator problem, so I'm not going to really write anything down. We're just going to kind of do it on the calculator together. Does that sound okay? Okay, so I'm going to go ahead and type in the function because it's asking to find the maximums and minimums. So to do that, I'm going to have to graph. I'm going to go to the y equals to type in the graph. So I have x times and then the absolute value. If you remember, we can, yes, sir.
Pretty sure. Are you going to go to like the math class?
Yeah.
Because I'm pretty sure if you go for a second 0 catalog, I don't know if this is on everyone's calculator.
It's probably the first thing on the list because it's alphabetical.
Yeah.
You could do that also. Yep. Yep. So I usually do math and then number, and it's the first thing on the list. It might be the first thing in the catalog. I don't remember. You could do it that way also. That's perfectly fine as well. And then I'll type in the rest of it. Any questions about where I got the absolute value from? Again, you can do math and then over to the number, and it's the first option there. Or Drake says, at least on his, it's the first thing in the catalog. So second 0 will open the catalog, and it may be the first thing in the entry there. I'm going to go ahead and graph this thing. I don't know. I was monkeying around with this calculator all day for different classes. So I'm going to graph it, I'm going to do zoom standard. So I'm going to do Z standard just to reset it back to kind of the normal window that we probably had our calculator set at from the last time we did something in class. So if I take a look at this, it doesn't appear that there's any maximums and minimums, right? When I take my first look. I'm a little suspicious about that in a problem where it's asking to find maximums and minimums. But it could be the case. The place I'd be suspicious about is this part right in here where it looks like maybe the graph flattens out. It might be a situation where if I zoom in, there's actually like a little in there or something. So I'm going to take a little bit closer look. Me, you good so far on my reasoning? Everywhere else, it looks like it's just like going basically, I mean, it's not straight, but it doesn't look like there's any opportunity to get a little anywhere. You guys get what I mean by a You know, just like a, okay. So I'm going to go and zoom in. I'm going to do this manually, though, because I feel like I'm smarter than the calculator sometimes when it picks how to zoom. If I look at my graph, since it's basically at the origin, it looks like where the action is. I'm just going to change my windows from, instead of -10 to +10, -1 to +1. And I'm going to change the scales to 0.1. I don't think I'll really need that. But if I have to zoom in again, it'll give me a better idea of like how much I need to zoom into. If I have the scales, I can tell kind of like, oh, okay, so maybe if I go from like 0.3 to -0.2 or, whatever. You get the idea, right? So I'm going to do that and hit graph again. Aha! There was a little da-da-da in there. And so now it'll be easy to find, right? Now, did you have to use the window that I used to get here? No. You could have done zooms and just done zoom in, whatever, how many times you needed to. You don't need the same window I do. You just need to be able to see the maximums and minimums. Everybody okay with that? Mia, would you be good to do it from here, or do you need to see the calculator steps? Okay, but with this one, you're good with the calculator steps to find the maximums and minimums. You're just like, I don't see anything. Where did you get those numbers from? Or okay. Hold on one second, Amy.
Could you just show real quick how to do it?
Sure. So let's find the maximum first. So that's this about right there. You agreed? So I'll press second and trace, pick the maximum command. The calculator is going to ask me 3 questions: left bound, right bound, and guess. So the left bound is going to be anywhere kind of over here. My cursors are already on that spot, so I'll just press enter. The right bound is going to be somewhere like over there. So just move over to there. That looks good. Press enter. And then the guess doesn't matter. Press enter again. So that looks like 0.25, comma 0.13 if I'm rounding to 2 decimal places, which I think was the request in the homework problem. Is that good? And then for the minimum, it's like the same thing, right? I think the minimum is like, what is that? That's like negative point, or it's probably 0.5 and 0, I think is what it comes out to. You might have gotten like 1 point whatever times 10 to the -7 or something as your y coordinate. Or, I'm sorry, let's just do it. I think it comes up when you do that. Just so we can talk about what's going on here. So left bound, like there's fine. Right bound, over there's fine. Guess, yeah. So when I do this, I got 2.7765, capital letter E, -7. What the heck does that mean when I have letters in there? Drake?
It's either too big / too small, or it's probably in the scientific notation mode.
Yeah, it's it. Well, my calculator's not in scientific notation mode. It's just giving me a really small answer in scientific notation, right? So this is like 0.000000277 yada yada yada. If I round that to 2 decimal places, it's 0, right? Now, remember how when we talked about this, the calculator's not actually doing the calculus to find these maximum minimums. It's doing like an approximation algorithm. Here's a case where its approximation algorithm had a little bit of leftover before it got to like, okay, stop. Like, this is good enough. This is really, that number really should be 0.5 and 0. And you can see that because if you plug in 0.5 into the function, it comes out as 0. It's just based on the programming on the calculator, the algorithm that it uses to find these maximums and minimums. It's probably programmed like we do this many, like you do it for this, either you get the exact answer or you do it until, this many times, and then you just stop and report back whatever it is you got because it's good enough. It probably, in this case, did it the maximum number of loops through that algorithm before it just said stop, that's good enough. And we had a little bit of left over because we didn't get quite to the, we didn't, instead of getting 0.5, we got real close. And instead of getting 0, we got real close. But if you're rounding to the 100th, you get the same thing as what you would have gotten had you done it exactly.
So basically, if you get a number like that, you just say 0.
Yeah, I mean, if we're rounding to do 2 decimal places, that comes out to be 0, right? Because you have 0.000000006 or 26 or whatever the, and if you're rounding to the 100th place, that just rounds to 0 still. You know what I mean? So it comes out to end up being the same number. The approximation algorithm will never be like crazy off. It might be like, okay, to the 7th decimal place, and then we have like a disagreement with the exact answer. But it'll be always really, really close like that. Mia, is that, we good? Okay. Amy, were you happy with what I did to get there?
I just show you. I got like 6.4.
Right, but does it still say e to the negative whatever at the end?
Yeah, it's just e to the negative 7.
Yeah, that's fine.
Okay.
Like here's the thing. I've done this problem 3 times today. I've gotten a different y coordinate each of the 3 times I've done it, because depending on where you started with your guess and what the window you picked, like the approximation algorithm just isn't finishing. So like the amount of leftover they have is going to be different depending on those 3 inputs.
Okay.
So that's the only reason why your answer and my answer are different, is because we picked different left bound, right bounds, and guesses.
Okay.
Which is like no big deal, right? Because it's, if you round to 2 decimal places, we still have the same answer. Does that make sense?
Yeah. Thank you.
So that's all that's happening on the calculator. It's purely a programming issue, is why you're seeing an answer that differs from my answer and why we're not getting the exact answer. If you had this thing let to run like an infinite number of loops through the algorithm, like it could just keep going until it finally finished, I think it would probably finish and not end up a little bit off, but it might have to run for like a month in some cases to finish. And I think that TI was like, you know what? We'll opt for the best we can do in like 3 seconds, which is probably good programming. Jack.
Is there any way you could do another like example of the odd even problem?
I mean, if you just make up a polynomial, we can do one.
Okay.
But before I get to that, I think Mia said she had 2.
I'm good now.
You're,
Yeah.
oh, never mind then. Yeah, if you just make up a polynomial, we can do it.
Okay. Actually, I can do number 20. I never got that.
Oh, you want to just do 20?
Yeah.
Okay, that's fine. No big deal. I'll do whatever you guys need, All right, so if I take a look at this one, again, before we start the proof, it's nice to know what we should be looking for, right? So let's look at the monomials one by one. X squared is degree 2. X is degree 1. Negative 1 is degree 0. So I have 2 even ones and an odd. This should be an either. Everybody agree with that? Let's just verify that now algebraically. So we'll always start with evaluate the function at negative x. So I'm plugging in negative x's. Now, important here, the order of operations matters. The first thing I need to do is the exponent. So negative x squared is positive x squared. And then I still have that negative sign floating out front. Everybody's okay with that? I can't do negative times negative right away because the exponent should come first. And then I have the negative x and the negative 1. If I compare this to the original, that's not h of x. So it can't be even. Jack, you good so far?
Yeah.
Okay. Once I've done that, okay, it's not even. Now I'm going to factor off a negative sign and see what I got. So if I compare this to the original, well, that's not negative h of x, right? The part that we underlined in green doesn't match h of x. So I can't have negative h of x. So it's not odd either. Since it's not even and not odd, it has to be neither. Does that feel okay?
Yeah, so when you're looking for odd,
Mm-hmm.
you're still comparing it to the original.
After you factor a negative off of it. Yeah. Yes, you factor the negative off, and then whatever's left, you compare to the original. The other option would be at the very beginning, you just write down what negative h of x is, and then you compare to that. You could do it that way also. I like doing it this way because it's not generating like extra stuff to compare to. I'm just always comparing back to that original thing. I have to cheat. I don't remember. It's not Luke. It was Zach.
How do you tell if it's even, odd, or neither just by looking at it?
Yeah, so you just look at if it's a polynomial, like all of the problems, not all of the problems, but 19, 20, and 22 were all polynomials. So if the degree is even for all of the terms, it'll be even function. If the degree is odd for all of the terms, it'll be odd. If you have a mix, it'll be neither.
Okay.
Drake.
Remind me, what does it mean when you say degree? Like degree, like.
So the degree of a monomial is the sum of the exponents on the variables. So the degree of x squared is just 2. The degree of x squared y would be 3, because you have 2 on the x and a 1 on the y. The degree of 7 would be 0, because there's no variable at all. Is that cool? Okay, when we say the degree of the polynomial, the degree of the entire polynomial is going to be the degree of the largest monomial, or will be the largest monomial degree, right? Because a polynomial is just the sum or difference of monomials. Okay with that? Okay. Did that clear it up?
Except for when you said like degree of 7, do you mean like there's no variable, like no x to it, or just?
Right. Yeah, so the degree of 7 is 0 because it doesn't have an x. It doesn't have a variable attached to it. So you could think of it out as like 7 times x to the 0, right? Because anything to the 0 power is 1. So like 7 times 1 is still 7. You can think about it that way too. Eddie.
So back on number 11, I'm just kind of confused how you got that the 4 and the -4.
Okay, just the bracket part?
Yeah, like the LDR is equal to FLDB.
Okay.
Yeah. Can you just go over that just one more time?
Sure. So what I'm doing, to find the range, I'm going to use the domain. Okay? So to find the range from the domain, I have to know whether the domain is increasing or decreasing and kind of when it's increasing and decreasing. So this function was a little bit weird because half of it was decreasing and then half of it was increasing. I only needed to use one or the other interval because I noticed that it's the exact same thing on both sides. So the y-coordinates are identical on either side of the graph. So I didn't really have to worry about both sides. I could just pick one or the other. Is that okay? Okay. So if I'm using the increasing interval, my lower bound for the range comes from the lower bound from the domain. So for that increasing interval, the lower bound was 0. So when I plug f of 0 back into the original function, I get 0 squared minus 4, which is -4. Similarly, when I plug when I plug infinity in for x squared minus 4, I get infinity. And because I'm finding an upper bound, the infinity is positive. If it was finding a lower bound, the infinity would be negative. Now, if I'd used the decreasing interval, the lower bound for the range is going to be f of the upper bound for the domain. They switch. And then the upper bound for the range would be f of the lower bound from the domain. if I'd used the decreasing interval. You could have done that also. That would have been fine.
So that'd be like opposite.
They switch. Yeah, they switch. You would get the exact same thing if you did it that way, because if you look at the interval, it's the same interval but reversed, right?
So in this case, it wouldn't matter.
It wouldn't have mattered. Yes. And to finish up, I know that the -4 gets a bracket here because I know -4 is in the actual domain, right? -4 is one of the all real numbers. So I know that the range value associated also has to have a bracket because it's also included, because it's coming from something that is included. So I can't go back and look at the interval that's increasing because that's not actually my domain. That's just like the domain of the increasing piece, right? Is that okay? Yeah, that's a tricky one. It was tricky. If you tried to do it algebraically, which it did not in this question require you to do, if you just looked at the picture and just found, okay, the range is going to be the lowest y coordinate, which was here at -4, to the highest y coordinate, which is positive infinity because I have an arrow pointing up. You could have been done that way also. Is that okay? Okay. Elvis. 13? Sure. So this one is just asking us to kind of interpret the graph or label the graph here, and then do the intervals. So I'm just going to kind of write on the picture. There's not really any work to show. It says state whether the labeled point is a maximum, minimum, or neither. And then identify the intervals where we're increasing and decreasing. So -2, 0 is like the top of a hill. So that's some kind of maximum. Because there's still the graph going up, there's definitely points that are higher than that. So it would be like a local maximum. And then 3, -2 is like the bottom of a valley. And there's still stuff lower than that. So that would be a local minimum. You good there? Okay. Then I'm going to go and label my intervals of increasing and decreasing. So if I think about my little person walking up the hill, I'm increasing here. Now my little person is walking downhill, so we're decreasing there. And then we get to here and we're walking back uphill again. So I have 2 intervals that are increasing and 1 interval that's decreasing. So far, so good. So my increasing starts here at the left end, so that's going to be -infinity. And it goes all the way to -2, 0. But all I care about is the x-coordinate. Oops. These intervals of increasing, decreasing are always described using their x-coordinates. And then my second interval increasing starts at this point, 3, -2. So we'll start with 3. And goes on all the way to the right, so positive infinity. And then for decreasing, we start at -2, 0 and go to 3, -2. Does that feel okay? Amos.
I don't have it.
Yeah, totally. No problem. Lexi.
Region number 17.
17? Sure. This is another all on the calculator problem. So I'll do x times the square root of x minus 1. And then I'm going to, do the zoom standard because I goofed with my window for that previous one. So just to get it to graph. So I look at this, it doesn't appear that there's any like hills or valleys, right? However, if I turn off my axis for a second, you'll see that there is a distinct starting point to this function. It doesn't start with like an asymptote or an arrow. There's a solitary point that is the beginning. Do you see that? That's going to be a global minimum, that single point. Right? Because that's the overall lowest point in the function. So I just have to figure out what that point is. Okay with that? I'm going to turn the axes back on real quick because I can probably just read it off the graph, it looked like. So it looks like it's the point 1, 0. Everybody, you agree with that? If I go back and I look at the function here for 17, just do that. Oh, you booger. Anything that's smaller than 1 would be undefined because I'd have a negative underneath the square root, right? So 1 is the smallest value that this function can take, or that the smallest x value I can plug into this function. Do you see that? So that's going to be the point furthest to the left, which is exactly where my minimum is going to occur, was the point furthest to the left. So if I plug 1 into that, it's easy to see that I'll get 0. So 1, 0 that I estimated from the graph is definitely confirms that that is the lowest point on the graph. Does that feel okay? So again, maximums and minimums can be the top of hills or bottoms of the valley, or if you have like a graph that isn't infinite in both directions, it could be like the start or the end of the graph if that point is the highest or lowest. Does that make sense? Are you sure? Okay. Okay. Feels like we did them all, guys. Anybody else takers on anything before we move on to the next thing? Okay. Can you guys, I think I can finish section 1.6 here because it's not much, because it's again relying on some stuff that we've done before or just kind of verifying some stuff numerically. So it's not so bad. Hopefully from last year, we remember that an asymptote is like an imaginary line that the graph approaches but never crosses. Does that sound about right? We had two kinds of asymptotes. We had vertical and horizontal asymptotes. And we also had like oblique asymptotes, like ones that were on a diagonal. Does that all sound familiar? At least when we talked about rational functions, probably all of these things came up, right? So let's just take a look at this picture. So I see what looks like a vertical asymptote here and here. Everybody agree? And maybe a horizontal asymptote here. Now, technically speaking, the horizontal is not actually an asymptote. Why not? Sergio? Yeah, so you notice in our picture here, the graph is definitely crossing that horizontal. So technically speaking, it's like just an end behavior and not an asymptote. We're not going to worry about that distinction right now. We'll deal with that in the future. But I think we at least in my classes, we talked about this when we talked about rational functions, the difference between like an asymptote and an end behavior. And I just want to acknowledge I am going to refer to this as an asymptote right now. even though it's not. But it's close enough, right?
What is it? What do we call it?
So it's an end behavior.
Oh.
It's just an end behavior. Because the ends act like an asymptote,
Yeah.
but the middle, there's some crossing going on. Is just, that's the more general term. So this function that you're looking at was y equals x squared plus 3x minus 3 over x squared plus 2x minus 3. Now you hopefully remember the vertical asymptotes were not too difficult to come up with, right? How did we find those? Do you remember? Yes.
Well,
Probably factored.
basically, it's not.
Yeah, so,
That's what I was trying to say.
okay, so you need the reduced denominator set equal to 0. So in order to reduce that denominator, things need to be factored. So you're right on there. If I take a look at the numerator, though, nothing is going to factor because there's not two numbers that multiply to give me -3 and add to give me +3. But the denominator does. +3 times -1 gives me -3, and it adds to give me +2. So applying the zero product property to the denominator, I end up with the vertical asymptotes of -3 and +1, which is what we confirmed visually, right? Do you remember how to get the horizontal asymptote out of one of these things? It turned out there's like 3 different cases. It got kind of confusing. There's like a lot going on. What we're going to do instead here is we're just going to kind of confirm this horizontal asymptote numerically. Okay? So the idea is that for a horizontal asymptote, as you get closer to positive infinity along the x-axis, the y value should be settling down to a specific number. Or if you're going to negative infinity, it should be settling down to the same number. Everybody's okay with that? We're just going to kind of confirm that with our calculator, and that's what we're going to worry about. So I'm going to go ahead and just type the function into my calculator. So I'm going to do the parenthesis and then the entire numerator. And then a parenthesis and the entire denominator. Got to make sure I put those parentheses in there. Everybody's okay with that? And now what I'm going to do is I'm going to graph this over the window from -1000 to +1000 on the x. And I guess let's make the scale 100 so we actually get some tick marks in there. Doesn't really matter. The tick marks don't really matter. And so I get a pretty boring looking graph. It looks like a straight line. Well, it's not really a straight line, but because I'm zoomed so far out, it's going to look like one. But that's fine. So what I'm going to do is I'm going to evaluate this function at when x equals 10, 100, and 1,000. And then at -10, -100, and -1,000. And just see what's happening to the y coordinate. And make sure that they're both settling down to the same number. Okay? So as x gets bigger, it should be getting closer to whatever that asymptotic value is. And as x gets smaller, it should be getting closer and closer to that asymptotic value. Everybody's good with that plan? So the easiest way to do this on our calculator is we can press second and trace and select the value command. So when x is 10, I have 1.08 yada, yada, yada. I'll go back in, second trace, I'll pick value again, but this time we'll say when x is 100, I get 1.009 yada, yada, yada. Getting closer to 1, right? We went from 1.08 to 1.009. And we'll do it one more time for 1,000. And here we have 1.0009. So again, smaller yet, right? So that's going to be our evidence that, okay, at least at the right end, it's going to 1. Everybody good with that? We'll do the same thing now at the left end. So I'll do second and trace, pick the value command. We'll do -10. So I'm at 0.87. And then -100. We're at 0.98. That's getting closer to 1. And then -1,000. And got 0.998. So again, closer yet. And that at this point I'm going to say is done. The horizontal asymptote is at y equals 1. That's the gist of the idea for this section. You look unimpressed. A couple of things with using this, the value command on our calculator, a couple of things I should point out to you about the functionality there. The viewing window is very important for the value command. If the graph didn't plot a point with that x value and you try to do value, it's going to give you an error. So remember, I made my window from -1,000 to +1,000. If I try to do value of 1,001, it's going to give me an error because that point isn't on my graph. It can't find. It's like, yo, dummy, I didn't graph this. I don't have a number to give you. It's going to give you an error. Doesn't mean you did anything wrong. It just means you're looking at a window that's too small. So that's why at the beginning, why I put in -1,000 to +1,000, so that I was making sure I was going to be able to get all the points that I was looking for. That's the big takeaway. This is how we're going to confirm a horizontal asymptote. It's just numerically. We're going to pick some test values and say, okay, that looks good. This is quite similar to one way you can, or at least the initial way in calculus that you'll evaluate a limit, which is a calculus operation that you'll see potentially next year if you're taking a calculus course. Well, you'll develop methods better than this after that, but this is like the starting point. Zach.
Since we didn't get through it all, is the homework going to be assigned?
So at this point, my plan today was at least to start 1.7. Obviously, that's not going to happen here. I put on Sunday's homework check is you're only responsible for 1 through 22. Anything from today is going to be into the Sunday afters, not this Sunday, but next Sunday's homework check. And typically, I'm going to try to do a good job this year of making sure you have at least one class day to ask a question before the homework check, or before something would be expected in the homework check. So anything that we would do on a Friday would not be due on Sundays, the next Sunday's homework check, but the Sunday after.
Okay.
Does that feel okay?
Yeah.
Okay. We're going to have to haul buns on Tuesday, though, to kind of catch up a little bit, because we're a little bit behind in not starting section 7 today, but we'll live with it. Just FYI, you guys could be able to do numbers 23 and 24, which is the only homework from 1.6.